Let's start by looking at this example. Which of the following is a redox reaction? And for the redox reaction, identify the oxidizing and reducing agent. Now, if I do a little bit of a recap, from the previous video, we know that a redox reaction is a reaction that involves a transfer of electrons. So you have a transfer of electrons from the reducing agent to the oxidizing agent. So based on the previous video, you can detect a redox reaction if there is a change in the charge of the substance. So one substance will have an increase in charge and the other has a decrease in charge. Now, if you look at the first example here, this is an acid-base reaction, and I think a lot of times if you write the ionic equation, it's a lot easier to tell that it's acid-base or if it's redox. So if I just quickly write the ionic equation here, this is an acid-base reaction because you can't really say that one thing has an increase and another has a decrease in charge. The two substances just combine to form water. So this is not redox, it's acid-base instead. And if you look at the second reaction, this is the reaction between magnesium and hydrochloric acid. So the pop test that we did, once again, if I write the ionic equation, you can actually see quite clearly that this is redox, even though this is the example that I used last lesson. So that's another reason why you should be able to tell. But the magnesium has gone from magnesium to magnesium 2+. So magnesium has definitely given 2 electrons to the hydrogen ion. So this is a redox reaction. And then when we look at example 3, this one is already an ionic equation, so you don't even have to simplify it yourself. And you can see that copper ions has changed to copper and zinc has changed to zinc 2+. So the zinc must have given 2 electrons to the copper ions in order for it to become a cation, and then the copper ions, as it received the 2 electrons, become neutral copper. So this is a redox reaction as well. All right, and now we get to number 4, and number 4 is probably the most interesting here because if you look at it, this is the combustion of methane gas. And so there's a reaction between methane or CH4 and oxygen gas to produce carbon dioxide and water. So the interesting thing about this reaction that set it apart from the other 3 is that there isn't any metal involved, and it is also not possible for me to write the ionic equation. So the question is it redox? I can't write ionic equation, and because there's no metal, you probably won't be able to detect any change in charge as well, because all 4 species in this case are covalent. So when you come across an equation of a reaction such as this, it's actually quite difficult to tell if it is a redox reaction or not. I don't want you to have the misconception that only metals can have redox reactions, because redox reactions can occur for covalent substances as well. It's just when you get to this situation, it's a little bit difficult to detect. So in order to resolve this problem, we develop a system called oxidation numbers. Now, oxidation numbers is also called oxidation state. And the first thing I want to emphasize is that this is a made-up concept. So it's a fictitious, man-made concept. So we came up with this, like it's in the human species. And it is created to provide a way to detect the flow of electrons in a redox reaction. So you would use oxidation number when, especially in the example that I just showed you earlier, when everything is covalent and you can't really tell whether or not there has been a transfer of electron, that's when oxidation number comes in. An oxidation number is assigned to each element in a substance, and it contains 2 parts. You have a sign, and then you have a numerical value. So, for example, positive 2 is the way that you would set out an oxidation number. So this is just to set it apart from charge of an element. Charge is normally the number comes first and then the sign, and then with oxidation number is the opposite. So this is the set of rules that you need to use in order to determine oxidation number for elements. So the first rule is this: the oxidation number of each atom in a pure element is 0. So for example, if I have Na, this is a pure element, so it just has sodium, then the oxidation number of this element will be 0. So I just put a 0 on top of the element. If I have oxygen gas, there are 2 atoms in oxygen gas, but this is still a pure substance. The oxidation number of each oxygen atom in this element is also 0. If I have, I don't know, S6, for example, so sulfur, again, this is a pure element. It only contains 1 element, so the oxidation number is still 0. Fe, maybe another pure substance, oxidation number still 0. Iodine, still 0, something like that. So the oxidation number of each atom in a pure element is 0. Let's look at rule number 2. The oxidation number of an atom in a monoatomic, now monoatomic just means that the ion contains 1 atom, so monoatomic ion, the oxidation number of an atom in a monoatomic ion is equal to the charge of the ion. So if I have a monoatomic ion such as Na+, so the charge of this ion is 1 plus, then the oxidation number will be the same as that, which is positive 1. If I have a oxide ion, so it's still a monoatomic ion, the ion contains 1 atom only. The charge of this ion is 2 minus, then the oxidation number, which is always written above the element, is going to be positive 2. If you have something like Cl minus, the oxidation number will be negative 1. If I have Fe3 plus, the oxidation number is positive 3. So the oxidation number of a monoatomic ion will be the same as the charge of the ion. Now these 2 rules are probably the most handy. In compounds containing oxygen, each oxygen atom has an oxidation number of negative 2. And then rule number 4, in compounds containing hydrogen, each hydrogen atom has an oxidation number of positive 1. So the first thing to keep in mind is that this only occurs in a compound that contains the element. So if I have pure oxygen or pure hydrogen, the oxidation number of each atom would still be 0, according to rule number 1. But if I have a compound, which means if I have a substance that contains multiple elements with oxygen and hydrogen being 2 of them, then oxygen tends to have the oxidation number of negative 2 and hydrogen has the oxidation number of positive 1. So a classic compound that contains hydrogen and oxygen would be water or H2O. So in H2O, each oxygen will have an oxidation number of negative 2 and each hydrogen will have an oxidation number of positive 1. I also want to point out that there are some exceptions, so this does not apply all the time. We'll talk about a little bit, I think 1 or 2 of the exceptions later. But if you see a compound, you should be able to, for the most part, assign the oxidation number of oxygen and hydrogen to be negative 2 and positive 1. All right, let's look at rule number 5. For a neutral compound or molecule, neutral means that it doesn't have a charge attached to it. The sum of the oxidation numbers of all atoms equal to 0. All right, I will show you a few examples. So let's say I have sulfuric acid, H2SO4, and I am tasked with determining the oxidation number for every atom in H2SO4. Now, according to rule number 3, oxygen will take the oxidation number of negative 2 because this is a compound that contains oxygen. So each oxygen atom is negative 2. According to rule number 4, hydrogen will take an oxidation number of positive 1. So each hydrogen atom will be positive 1. So you have negative 2 and you have positive 1. And then you should be able to use this information to work out the oxidation number of sulfur. The one thing to keep in mind is that the number that you write on top here is the oxidation number of 1 atom for the element. So if each oxygen atom has an oxidation number of negative 2, then 4 oxygen atom will be 4 times negative 2, which is negative 8. So that's the total number you get from oxygen. So if each hydrogen has an oxidation number of positive 1, 2 hydrogen will be 2 times positive 1, which is, that looks like a 4, which is positive 2. So the oxidation number of sulfur, I don't know what it is, but I'm just going to call it X. So 2 plus X minus 8 is supposed to equal to 0. This is the sum of all of the oxidation number, which is 2 plus X minus 8, and it would equal to 0 because this molecule is neutral. It doesn't have a charge. So this is the same as saying X minus 6 equal to 0, so X would equal to 6. So the oxidation number of sulfur in this case is positive 6. Let's go through another example, or at least a few more. I'm going to go C8H18. Maybe not a good idea. Let's do C6H12O6. I'm already regretting that, but we'll do this and then we'll do another one. So this is glucose, and once again it's a compound. So we're going to assume that the oxidation number of oxygen is negative 2H. So 6 oxygen will have an oxidation number of negative 12. Hydrogen, each hydrogen is positive 1, so 12 hydrogen will be positive 12. And let's just assume that the oxidation number of carbon is 6, so I have 6x here. And 6x plus 12 minus 12 is supposed to equal to 0 because this molecular compound is neutral. So 6x equals to 0, which means that the oxidation number of carbon in this case actually 0 already. So even when it is in a compound, it is possible for the oxidation number to be 0 if everything else have already cancelled each other out. Let's do one more. We're going to do vinegar. So vinegar is C2H4O2, which is the molecular formula. So oxygen is negative 2H, so 2 oxygen is negative 4. Hydrogen is positive 1H, so why do I keep doing this? Okay, each hydrogen is positive 4, so 2x, positive plus 4 minus 4. I wonder whether I've actually done this correctly. Yes, no, that's correct. Equal to 0. So once again, oxidation number of carbon equal to 0 in this case. You know, I don't like this example. I'm going to pick one when it's not 0. Let's do... What can I do with this one? I can't think of anything at the moment, which is not good. Oh, actually, yeah, no. Let's do this. It's not the best, but that's fine. So CO2. So the oxidation number of oxygen is negative 2 here. So 2 oxygen is negative 4, which means that carbon must be positive 4 because the oxidation numbers of the two elements have to add up to 0. So X equal to 4. Okay. Yeah, I can come up with better examples when we get to this one. Rule number 6, for a polyatomic ion, the sum of the oxidation numbers of the atoms equal to the charge of the ion. So polyatomic ions means the ion contains multiple atoms in it. So for example, if I have okay, let's do something that is like NO3 minus. This is a polyatomic ion, nitrate ion. So there are two different types of elements, and there are multiple atoms in the ion. So this is also a compound. It contains two different elements. So we're going to assume that the oxidation number of oxygen is negative 2. So 3 oxygen is negative 6. And I don't know what the oxidation number of nitrogen is, so I'm just going to call it X. So I know that X minus 6 has to equal to negative 1 because this is the charge of the ion. So the charge is negative 1. So the sum of all the oxidation numbers of all the atoms has to equal to negative 1. So X must equal to positive 5. So that's the oxidation number of nitrogen in this case. Let's do another one. So if I have dichromate ion, Cr2O7, 2 minus, then the oxidation number of oxygen I'm going to assume to be negative 2. So 7 oxygen is negative 14. I don't know what the oxidation number of chromium is, so let's just assume that it's X for now. But 2x minus 14 must equal to negative 2, which is the charge of this ion. So 2x is 12, so x is positive 6. So the oxidation number of each chromium atom in this case is positive 6. All right, let's just do 2 examples for now. And then last but not least, in a compound, the most electronegative atom is assigned the negative oxidation number. So you have to do this when, this is mainly for the exceptions for rule 3 and 4. So if I have something like NaH, hydrogen metal hydride, NaH, then even though hydrogen usually takes a positive oxidation number, in this case, hydrogen is still the more electronegative element because sodium is just not. So the metal will be positive and the hydrogen will be negative. Can you say that hydrogen is more electronegative? Anyway, the metal should always take the positive oxidation number if the metal is combined with a non-metal. And another example is hydrogen peroxide, H2O2. Hydrogen will take the positive oxidation number, and in this case, oxygen is actually going to be -1 because in order for the total of all the oxidation numbers to be 0, the oxidation number of oxygen has to be -1 here. So this is another example that you need to keep in mind. Oh, it's one of the exceptions to rule 3. All right, don't worry too much about the exceptions otherwise, besides the 2 that I just gave here. We don't look at the exceptions very often in this course. All right, so let's talk about how we can use oxidation numbers to determine a redox reaction. In general, if you detect a change in oxidation number going from reactants to products, then the reaction is redox. More specifically, if there is an increase and a decrease by 2 different species most of the time in oxidation number, then the reaction is a redox reaction. A decrease in oxidation number indicates reduction, and an increase in oxidation number, that should say number here, indicates oxidation, okay? And then we can talk about the conjugate pairs. I think I'll probably mention it a little bit later, but it operates the same way as a conjugate acid-base pair. So the oxidizing agent will be turned into the conjugate reducing agent, and the reducing agent will be turned into the conjugate oxidizing agent. Let's go back to the example at the start. Which of the following is a redox reaction? Now, I know that we have determined that 1 is not, and 2 and 3 are redox, and we're not sure about 4. But let's say I'm going to use oxidation number to find the to determine this question from scratch. So I'm going to find the oxidation numbers of everything in all the equations. So the first species here is NaOH. Now, NaOH actually will follow rule number 2 and number 6 because NaOH is an ionic compound. So keep in mind that NaOH consists of Na plus and OH minus. So the oxidation number of sodium is going to be +1 because that's the charge of the ion. And in the case of OH minus, I think if you do oxygen being -2 and hydrogen being +1, that should suffice because if you add -2 and +1, you do get the charge of hydroxide ions. Okay, HCl, this is a compound, so hydrogen will be +1 and Cl is -1, so that they add up to 0. NaCl is another ionic compound with 2 ions, Na plus and Cl minus, so sodium will be plus and chloride will be minus. And H2O is a compound, so each hydrogen is +1, each oxygen is -2, and it will work because if you add these together, you do get 0, which is the charge of the compound. So you can see here in example 1, there isn't a change. Really can't speak today. There isn't a change in oxidation number at all going from reactants to products. So the sodium start with +1 and end with +1. The oxygen start with -2 and end with -2. And hydrogen just stay +1 and chloride just stay -1. So if you see no change in oxidation number, that's an indication that it's not a redox reaction. So no change in oxidation number is not redox. Now if you look at example 2, now we know that this is a redox reaction from the ionic equation, but you can also find oxidation number. So magnesium is a pure substance, So according to rule number 1, the oxidation number is 0. Hydrochloric acid, once again, it's +1 and then -1, so similar to above. This is hydrogen in a compound. When you get to magnesium chloride is an ionic compound, consists of magnesium ion and chloride ion. So the oxidation number of magnesium will be +2 and of chloride will be -1. And hydrogen is a pure substance, so in H2, so the oxidation number of hydrogen is 0. So you can see here that there has been two changes in oxidation numbers. Magnesium has gone from 0 to +2. So Mg has gone from 0 to +2. So there is an increase in the oxidation number of magnesium, which means that it has undergone oxidation. And hydrochloric acid or hydrogen has gone from +1 to 0, which means that hydrogen has undergone reduction. So if magnesium has undergone oxidation, then it is the reducing agent. Remember that the reducing agent undergoes oxidation. And if magnesium is the reducing agent, then Mg2+ is the conjugate oxidizing agent of Mg. Okay, so it's very similar to conjugate acid-base pair. The hydrogen in HCl is the oxidizing agent. So oxidizing agent is hydrogen, which means that H2 is going to be the conjugate reducing agent of H+. Okay, so that's how you would find this out. So if there is an increase in oxidation number, then the substance has undergone oxidation and the substance itself is a reducing agent. If there is a decrease in oxidation number, the substance has undergone reduction and the substance is an oxidizing agent. So let's go to number 3. Number 3 is probably the easiest one here because this is already an ionic compound. So the oxidation number of copper 2+ is +2, going to 0, 0, +2. There's not much to this, but you can see again a change and an increase and a decrease in oxidation number. So the copper has gone from +2 to 0. So copper 2+, wow, this is reduction, and a decrease in oxidation number. So copper 2+ is the oxidizing agent. You definitely do not need to use oxidation number to work this out, but we're trying to work to practice this skill. So if copper 2+ is the oxidizing agent, then copper is the conjugate reducing agent of copper 2+, and zinc is the reducing agent So zinc 2+ is the conjugate oxidizing agent of zinc. The concept of oxidizing reducing agent pair will become very useful and important later, maybe next week. I really hope I have enough room to write this, but okay, maybe not. And here I thought that I have left enough room for the oxidation number on top. Okay, let's just squeeze this in very tiny. All right, last one. Now let's talk about this example. This is our original example where it was really difficult to tell whether or not it was redox because there is no metal and you can't see any change in charge. And this is where oxidation number really shines. So I'm going to find the oxidation number of everything. CH4 is a compound. So I'm going to assume that hydrogen is +1. You have 4 hydrogen atoms. So the oxidation number of carbon +4 must equal to 0, which is the charge of the compound. So carbon must be -4 in this case. Oxygen, O2, is a pure substance, so the oxidation number of oxygen is 0. In CO2, each oxygen is -2, so the 2 oxygen would be -4, and then they have to add up to 0 again. So in this case, the oxidation number of carbon is +4. And then lastly, I have H2O. Oxygen is -2 and each hydrogen is +1. So let's try to observe this and see whether there's any change in oxidation number. Carbon has gone from -4 to +4. So carbon has undergone oxidation. There is an increase in oxidation number for carbon, so it's oxidation, which means that the carbon in CH4 is the reducing agent, and CO2, which also contains carbon, is the conjugate oxidizing agent. Oxygen has gone from 0 to -2, so 0 in O2 and then -2 in H2O. So oxygen has undergone reduction, and O2 must be the oxidizing agent. And H2O, the O in H2O is the conjugate, or H2O really, conjugate reducing agent of O2. Okay, so whenever you see covalent substances in an equation, oxidation number is probably the best tool that you have to determine whether or not the reaction is redox, but also to determine which one is the oxidizing agent and which one is the reducing agent. All right, and let's try these two questions, and good luck. Thank you.